Okay, so welcome to Alum at Alma talk series. Today's talk is going to be from our alumnus Manas Thakur. He's currently faculty member at CS department at IIT Bombay. His research interests include program analysis, compiler optimizations, programming languages, software engineering, and parallelization. Manas is a PhD graduate as well as a master's degree he received as a joint degree from CS IITM. His thesis, Precise and Efficient Analysis of Java Programs, won one of the Institute Research Awards and also jointly the IBM Best Thesis Award in 2019-20. Prior to IIT Bombay, Manas was at IIT Mandi for 3 years, where he also received a Teaching Honor Roll Award in 2021. In recent years, Manas has been a reviewer for various journals like TOSEM and Transactions in Software Engineering, as well as conferences CC, CASCON, and ISEC, and the workshop on software engineering SERI. Manas's research group at IIT Bombay is named Compel. I hope I had the right pronunciation. More than this formal introduction, I wanted to convey that we had very good interaction with Manas when he was part of the PACE lab, and one of the very bright and very sincere people in the lab. I also was fortunate to have Manas and Aman as my TAs in one of the program analysis courses, and that was very different experience in the sense that the work just got pulled from me rather than me pushing the work to the TAs. So yeah, so it's very nice that Manas has found time to talk to us about his work. The stage is yours, Manas.
Good evening, everyone. Thank you, sir, for such a great introduction, and uh, you related the kind of academic interaction we had while being a PACE lab member or a TA in your course. I would also add that I used to have a very good non-academic interaction with Rupert sir as well. I used to bother him a lot, and every time it was really useful. So thanks for inviting me for this talk, and I welcome all of you here. I share the screen quickly. I'll start the talk.
Yeah, it's
So,
visible.
sure. So we'll be talking about optimizing object-oriented programs. The example in case would be Java and Java virtual machines, but most of the techniques that we would talk about today would be are applicable across different kinds of O languages and the kinds of optimizations one could perform for different O languages, programs written in various O languages. Okay. So many of us know that O languages are very popular. I am sure almost all of you would be writing programs in C++, Java, C Sharp, or one of the object-oriented languages out there. So you should be able to find lot of synergy with what we would discuss today. You see three logos here because the part of some work that I would talk about has been done at IITM or is being done in collaboration with IITM. Some part of it was done during my tenure at IIT Mandi, and of course, the current work is being done at IIT Bombay. So that's why you see three logos over here. I belong to all the institutes, I would say. So what's special about O? Let's begin with what all do we associate, what all terms and what all features, what all characteristics do we associate with O programs in general. So you all know these terminologies, right? Abstraction allows designing programs in terms of real world objects and ideas. We can talk in terms of cars and robots and um, monkeys instead of just talking about their components. It allows us to abstract out and increase the level of abstraction at which we can talk about in our programs. Encapsulation hides internal details from the outside world. The outside world need not know what is the internal structure of a class. Inheritance provides us the ability to share common characteristics. So I could talk about a car and a truck that have similar characteristics instead of writing code again and again. And polymorphism allows varying behavior through dynamic dispatch, like in iPhone 15, right? You can, that new feature, you can program that button, what should pressing that hardware button do. So based on the setting, it would dispatch to a different routine that could allow you to either mute your phone or take a picture, whatever. Right. So all these characteristics in a sense depend on interaction between objects. In O programs, objects interact with each other by passing messages to each other, and the right message is dispatched, or basically the right method in O terms is dispatched based on the runtime type of the receiver, this pointer rather. Right? So it really depends on what is the runtime object, and based on it you call in the right method at runtime while program is executed. Right? Then what's problematic about O? Much of what is good about programmability is bad about performance, as we would notice now. Like when you have classes, you have an additional layer around primitives. At the lowest level, you only have primitive variables, and you have abstractions around primitives. Like you have additional layers. You have to incur an additional level of indirection in order to access a primitive field if it is if it is enclosed inside a class. Right? There is more allocation cost because now you have objects, you have to find memory. These objects can grow in size, so you have to find out the best fit for an object in the memory at runtime and so on. So allocation has its own costs. Uh, the way we write O programs most of the time introduce typecasts. We have methods and we do not know which method is called at runtime. Well, that's a feature, it's a polymorphic call, but I do not know which method is called, which means I cannot inline the method. If I cannot inline a method more often, I cannot perform much of an optimization across method boundaries. When I say I, it's rather the compiler. The compiler cannot optimize code across method boundaries in presence of polymorphic calls. Basically, you have less optimization, more cost, right? And in essence, we could say O is good for programmability, but it's often bad for performance. You can interrupt me anytime and ask me if you have any questions, by the way. So now let me instantiate this O with Java, right? So can anybody tell me quickly what do you know about Java that makes it really unique? Why did people start loving Java in, let's say, early 90s when it became popular? You can type in and, or speak out quickly. No issues. So I'm sure the word coming in many of your minds that you are hesitant to type in is platform independence, right? Portability. So Java became popular in 90s because at that time people at the same time internet became really popular. People were writing programs that could be transported over the wire, run on different systems, and so on. And Java offered this nice way of writing programs such that you can generate platform independent bytecode on your laptop, let us say, and run that bytecode anywhere where you have a JVM installed, not on your phones, desktops, even clouds, and so on. Right? Then another reason Java is popular is strong static typing. You cannot fool the compiler easily. You cannot just typecast anything to void star and back to something else. Such invalid typecasts are disallowed by the compiler. If a compiler disallows something, that means the actual program, when it runs, may have fewer errors, so you get happy users. When we start writing Java programs, we do not get sec faults, which really troubles a C or C++ programmer quite often. You get a sec fault and then it's just a sec fault. It doesn't tell you what is it about. You have to use GDB, you have to use printfs and find out where did you dereference some invalid memory. Whereas in Java, you would get these nice exceptions with stack traces. Where did the control flow and how did you really reach the point where there was an illegal access, let us say, a null pointer access, let us say. Then one of the most liberating features I would say in Java is automatic memory deallocation. You never need to free memory. It's just done automatically by the JVM. So there is garbage collection built in, which really unburdens programmers from the task of thinking about how is memory allocated and when should it be deallocated and so on. But then similarly, there are problems about Java as well. And interestingly, all the problems are related to the features that I pointed out a few seconds ago. Like, well, Java bytecode is platform independent, but it is very high level. What does it mean? The static Java compiler, Java C, that generates bytecode cannot really perform too many optimizations. It doesn't have any knowledge of the machine while generating the bytecode. So the static Java compiler cannot optimize your code much. That's a problem. Then strong static typing was good, but it means that you cannot really utilize your skills to directly talk to the memory and write faster programs like you could do with C or C++. You cannot manipulate memory directly. You cannot talk in terms of addresses. uh, Exceptions actually require a lot of runtime overhead in order to give you such a nice stack trace. So even giving good errors has its overhead. And then automatic memory deallocation, garbage collection really has its overhead. So in JVMs, in typical JVMs, GC is run as a separate thread. But even if you are running it as a concurrent thread, that's removing one thread from your program, first thing. And then there are times when that thread also requires your program to pause. You would notice that if you have a high memory consuming Java program, you would notice there are pauses, and those pauses are very unexplained, right? You do not know why does your program suddenly pause, suddenly stop printing output, and then resumes after a few seconds. So GC is good, but it has its own overhead. So, having looked at the good things and the bad things about O and Java, Java being one of the best examples of O programming per se, we know that Java bytecode, once generated, are executed inside a JVM, right? Java Virtual Machine. So let's also look at the fact that in presence of all the kinds of overheads that I mentioned to you about, even in the presence of such overheads, Java programs run pretty fast. So the JVM must be doing something really interesting with your Java programs. That's one thing that we would get familiar with in the next few minutes. So the question is, why isn't Java slow? Well, if you feel that Java is actually slow, let me give you a demo. This is probably the only time I need to switch and share a different screen, different window. So just bear with me for a few seconds. I hope you can see the terminal. Can anyone please confirm? Is the terminal visible? Terminal window. Hello, hello. Okay. Thanks, Marojan. Thanks, Brian. Okay. So here is a C program. Okay. Don't try to really understand what does it do. It has 3 for loops. I'm going to demonstrate to you that Java programs are not slow. Let's see. So you have a C program here where I have 3 for loops. 3 for loops are not really uncommon. You have matrix multiplication. You write nested for loops all throughout. Lots of computations, image computations involve nested for loops. So there is some program, and I'm doing some computation at line number 16. Basically, the important point to notice is each for loop runs through n times, where n was a program input, an input taken from the user. So here n is really the field n of the structure A that's populated using the command line argument supplied by the user. And then I run each of the loops n times nested inside each other, get some result, and I print that result at the end. Some random computation, representative random computation. Now I have a C++ program very similar. I have tried to reproduce it as faithfully as possible. A very similar C++ program. Instead of a structure, you have classes here, and in the main function, as you can see below, I print the result after computing it inside the method foo in the same way as I did in the previous program. I also have a Java program that does the same thing. I print the result at line number 5 in the main method. Right? I also have, for the sake of completion, since Python is very popular, I also asked one of my students who is a good Python programmer to give me an equivalent of the same computation in a Python code. So this Python program also does the same thing. All are supposed to do the same thing, and I have a script here that takes in the number of times each loop should be executed, passes it as a command line argument, runs the Python, Java, C and C++ programs, and tells me how much amount of time did the program take. I hope no questions, no confusions in this. So I'm just running those 4 programs, and let us just run a sanity check. So if I pass in 10, each loop will run 10 times, the innermost loop will run 1000 times, and the Python program took 0.036 seconds, C program zero point 0.2, C++ zero point 0.2, Java program 0.04 seconds. Right? So it works. Just to make sure. Now, we are not really interested in very small running programs. We would find it interesting when the programs run long, which language program runs faster, right? Like an input of 100 shows me that it's still competitive. Python is slightly slower, but okay, all are still less than 0.1 second. Let's make it 500. I'm sure you all know that Python is an interpreted language by default. I'm running it using the default Python implementation, which means there won't be any optimizations performed. So as expected, you can clearly see the Python program is super slow here. C++, Java programs are compiled and hence they are faster. So fine, this is as expected, but towards the end you should notice something interesting. The Java program seems to be faster than C and C++. This is different from what you were told in your childhood, isn't it? Let me do one thing just to save our time. I'll run on one more larger input, but I'll remove Python so that we are not wasting our time. Let me run it 1,000 times and see does the trend follow. Does the trend continue? See, yeah, Java is still fast. Okay, last 1500. Beyond that, you would start yawning.
Uh,
See, sorry, somebody was saying
uh,
something.
I'm sorry to interrupt, but uh, can you please go to a shell script for a moment?
Yes, sure, I'll go back. Sure, Hari. So if you see here, the speed up of the Java program also looks good enough. Right? The Java program is fast enough. I'll go back to the shell script and I'm not using any special arguments here for Java, C, C++ compilers. Hari, is there any other
So,
question that you had?
is there any reason you're not enabling optimizations for C, C++?
Yes, because I am not enabling optimizations even for Java. That's the only reason. I'll answer your question in more detail as I proceed with the talk. So it's a good observation that I'm not enabling anything special for C and C++. So whatever is the default optimization level, but then I'm not doing anything special for Java as well. Java also has optimization levels. So it's just the default run. We'll talk about optimization levels soon. Is that fine?
Okay, thank you.
Sure. Okay, so the observation we wanted to make here is that Java programs are competitive. Sometimes they may even be faster. Some programs may run faster than equivalent C++ programs, for example. That's one observation, and then with that observation in mind, let's come back to where we were. Okay. So Java isn't really the slow or the slowest language among the four of them, as it was doomed to be in early 90s. People just felt Java is supposed to be a slow language, but it's no longer a slow language. There has been a lot of advancement in the Java compilation technology inside JVMs in the last 20 years, and that makes it really fast sometimes. So the interesting part here is Java was slow when it was just plainly interpreted inside a Java virtual machine in the form of a stack over a stack. Right? But nowadays, or rather not nowadays, from last 25 years, Java is also compiled just in time. So Java bytecodes may not just be interpreted inside the JVM, but they may also be compiled by built-in compilers while your program is already being interpreted by the JVM. So let's understand this interesting mechanism in a bit more detail. So we'll pick an example from Hotspot VM, which is the default Oracle implementation of the JVM that most of us might have installed on our desktops or laptops. So what happens is your program is from the main method, right? When you start executing your the bytecodes corresponding to the main program in a JVM, it starts off with interpreting these bytecodes. Interpreting this, okay, you are just executing line by line inside the VM, right? It's supposed to be slow. Then what happens is we keep doing some special profiling. We keep determining which portions of the code of your Java code are executed frequently. They are called hotspots. Okay? How can we find out which portion of your code is executed frequently? We have to count something, right? So the interpreter will also profile your program. It will count how many times a method is called. It will count how many times a loop is iterated over. A loop is represented by a package here. So how many times a loop is executed, how many times a method is called. Based on it, it identifies, the JVM identifies hot portions of your code. Okay. Once it identifies some portions as hot or frequently executed, it inserts them into a compilation queue. So there is a compiler thread, or there are multiple compiler threads that are sitting behind the scenes, waiting for something to come inside their queue. Once the compiler thread finds something in its queue, it will pick an entry and it will compile it. That's why it's called just-in-time compilation. JIT compilation happens when your program is already executing in the VM. So a parallel thread will pick up some piece of code, try to compile it in the background, while the interpretation of the remaining bytecode continues. Your program will continue executing. Okay. Then, as soon as let's say I found the method foo is executed very frequently, and I gave it to the JIT compiler. The JIT compiler compiles it and makes the compiled version ready. Once the compiled version is ready, I don't need to interpret it because I have a faster, probably faster version available, more optimized version available. I would switch over. I would change the entry point of that code, whether it's the beginning of a loop or beginning of a method. The next time I call that method or next time I iterate over that loop, I would go and run the compiled, the more optimized code instead of interpreting the bytecodes. That's how we may get performance later on compared to initial slow runs in the interpreter. Right? So there is a lot of engineering that goes behind. I won't go into the detail, but this process is called on-stack replacement. Basically, some portion of your code, let's say, is on the stack, is on the runtime stack, and next time you are changing the entry point of this code, you are displacing this code. You might have computed some intermediate values of variables inside the loop and so on, and now you are going to the compiler environment. You are running it on the machine, the assembly code for the machine on which you are executing the program on which the JVM is installed, and hence there is a lot of interesting data transfer that should happen from one environment to another, and this is done in a very interesting way. So this is called OSR, and I encourage you to find out what all does OSR involve. But yeah, there is a process through which you can switch from interpretation of bytecode to execution of JIT compiled code. That's the point I wanted to make here. So, and what happens is there is not just one level of compiler here. So as Hari was mentioning in the big Naveen is, I think Naveen is your name. So as Naveen was mentioning in the beginning, we have optimization levels in various compilers, right? So inside the VM as well, you have multiple levels of compilation. So zero, if your method is being executed at level 0, that means it's just in the interpreter. Level 1 means you have given it to a compiler called as C1, the client compiler or the C1 compiler, the first simple compiler, small compiler, let's say. Then if you find that method is still getting executed too many times, you might send it to the next level, let's say level 2, where you again start profiling and finding out, counting how many times is this method being called. Then at level 3, you may do some more extra profiling. Well, if you can count how many times a method is called, you can also count how many times a branch is taken. How many times a loop, how many times, let's say, an object is of a certain type. A variable is holding an object of a certain type. You can count more interesting things. If I have a method call, I can count how many times did the virtual call lead to the method from class A versus the same overridden method from class B. Let us see. Okay. So there is more profiling that I could do at level 3, and at level 4 I have the most sophisticated C2 compiler, the server compiler, the bigger compiler which performs many more optimizations than the previous compiler is sitting at level 2 at level 4. So there are many of these levels of compilation, and your program or some portions of your program may be executing at different levels as you run your Java program in the JVM. So this is called tiered JIT compilation inside Hotspot JVM. Now, let's talk a bit more. We have understood about how to count a number of times a method is called and so on. Let's understand in a bit more detail what is this extra profiling and what optimizations can I do in a JVM based on this extra profiling information that I cannot do in static compilers like GCC and G++. What is really new that a JIT compiler for languages like Java can do that static compilers for languages like C and C++ cannot do. Okay. So let's look at an example here. I have a method foo that takes two parameters, an integer parameter a and an x parameter o. Then I do some addition. I have a method called o.bar. I return c at the end. And let us assume I have three classes x, y, and z, each of which uh, defines the method bar. Okay. So notice I had a call to bar inside foo, and which bar is called depends on the runtime object, the type of the object that is pointed to by the variable o. If o points to an object of type x, x dot bar will be called. If O points to an object of type Z in certain invocation of foo, then Z dot bar will be called. So different values may be returned by bar based on which method is called. And A is also a parameter, so different calls to foo may have different values of A. So let us say the JIT compiler decides to profile what is the value of A. If it profiles, let's say it counts and finds that last 10,000 times the method foo was called, 9,990 times the value of A was 10. And if I know this, I could speculate that it's always going to be 10. Let us see how. Let us say I remember I send this code to a JIT compiler and I remember that A is always going to be 10. I am making an assumption here that A is always 10. If I make this assumption, what could I do? I could perform constant propagation. I could say if A is 10, then B has to be 20. And instead of B, I could use 20 over there. I have performed constant propagation. I have avoided an addition operation over there. I have optimized the code based on an assumption. The assumption was made based on the runtime profile of the program. Right? If I could observe what is A, I could also observe what kind of an object is O. Let us say I again do profiling and find that most of the times O is pointing to the object, an object of type Y. If it is pointing to an object of type Y and I make this assumption, I could optimize the code further. I know the target of O dot bar. I could inline that bar. I could inline Y's bar, replace the result of calling O dot bar with 2, and now I know the value of C, so I can perform further constant propagation. And what do I get now? I have this method foo, which doesn't have a method call, which doesn't have an addition operation from the previous code, and I have also propagated some constants. It just has single statement return 40. Let us say I get an equivalent binary of this code by the JIT compiler. So I have a binary now that just returns 40. It doesn't know anything about calling bar, it doesn't know anything about adding A plus 10 and so on. Right? The only catch is this binary is compiled under the assumption that A is 10 and O dot type is Y. O dot type equals Y. What did I get? I got a much more optimized binary than the binary I would have generated for the original piece of code. And this I could not have done unless I made these assumptions. And I would make good assumptions, I would make good guesses, good speculations if I have gotten the information from the runtime profile of the program. Probably it's going to be true for the remaining program, in which case I can keep using this optimized binary that I generated just now. I'm sure some of you would be thinking now, we compiled and created a specialized binary under certain assumptions. What if later I call foo and I don't pass 10, I pass 20? I don't pass a Y type object, I pass a Z type object. So the assumptions would fail. Right? If the assumptions fail, the interesting thing is I cannot run this binary. The binary doesn't have, let's say I had an if else condition inside a function and I removed the condition check and the if branch, assuming that it's always the else branch that's taken. So my code may be more optimized, but that binary is not valid if the condition under which I compile the code is not going to hold true, right? So this is again a food for thought for you. Let me just mention that there is a process called as de-optimization. It has lots of interesting research directions, in fact. Where that process of de-optimization allows you a fallback option in case your assumption goes wrong. It de-optimizes the code in terms of the fact that it throws away optimized code and comes back to something else. Think about what all options you have when you want to throw away this equivalent binary that's invalid to be run against a certain call to foo. Any questions at this point? I'll go deeper into some of my work after this, but is there any general question at this point we can take? Okay, I think all of you are with me.
I have a question.
Yes, please.
So, you're assuming that B is likely 20, right? In the first step.
I assumed A is likely 10. Once I
Okay,
know A is likely 10, I automatically get B's value as 20. Yes.
so is there a separate thread in the JVM which is actually looking at what the values of the variables are.
Yes, so I could tell the JVM, well, it's an interesting thing to tell the JVM what all do I want to profile. And the JVM determines, let us say that it would be interesting to remember or keep noting down the values of A and the type of O. Let's say it found out from input, some input from the programmer or some heuristic skills built inside the VM. And yes, there is a separate JVM thread that would keep recording these values while the program is executing.
So it's something like keyword which you mentioned for a variable, and those variables are being kept track of.
See, by default, there is no such keyword, Naveen. By default, the JVM would just do it for interesting scenarios. And by interesting, it means, let's say a method is really hot, then it would start trying to profile various informations about that method. But
Okay.
of course, people have tried to tell the VM what should it definitely profile. What should, in fact, one of my students is trying to tell the VM what should not be profiled so that you can reduce the profile overhead possibly.
Thank you.
How long does profiling take? Is it possible that application becomes faster later than in the start? That's right. So typical any language that uses a JIT compiler, right? It's the problem is called cold start problem. Initially, your program will run a bit slow. Hence, let's say you are doing a research work involving a program that you are running in a JIT compiler based system. What you would do is you would ignore the initial runs saying they are warm up runs. The program is just getting warmed up because the machine is actually trying to figure out which portions of your code are hot and so on. So yes, there is an overhead. It pays off. It pays off very well. Not only in case of Java, but C Sharp, R, PyPy for Python, all the JIT compiler implementations that are out there. JavaScript, Google V8, everybody uses a JIT compiler nowadays. All right, let's proceed
So
ahead.
profiling be possible in a static compiler like C in any scenario.
You could, but then what would you do with the profiling information, right? You could get the information, feed it back to the compiler and create a more optimized binary, but you cannot speed up the same instance of the program and change the compiled code unless you have an instance of the compiler in place in memory while your program is still running. Does that answer your question, Pranav?
Yes, sir. Thank you.
Okay. So what's problematic? Rupesh sir, you were saying something?
Yeah, I was just wondering that during compilation we might also not have the inputs available.
During compilation, the static compilation, you mean?
Static
Yes,
compilation, yes. I mean,
yes, yes.
answering Pranav's.
Right, that's right. Thanks. Okay,
There are
so
there are some tools to have JIT compilation also in C, C++. So I'm not sure. Maybe that's what Pranav was asking.
no, Pranav, I believe was pointing out to the fact that you could probably run things, get profile, stop the program, and then take it back and discuss it and include it while compiling C code statically. But yeah, there are multiple options. Of course, all of this can be explored. In fact, there was a thread last year. I think it died, but there was a thread where a group of people proposed to the C++ community. There was a mailing list where they had posted an idea of building a full-fledged JIT compiler for C. I'm not sure what happened to it, but yeah, of course, there would have been people who have tried in smaller amounts and so on. Okay. So, I mean, many of you understand the problems with JIT already, right? It allows us to perform these speculative optimizations. It's very powerful because it has some idea about runtime values. But then the time that you are spending during JIT compilation is directly affecting the execution time of the program, isn't it? As a result, most JITs, so you know, right, in order to optimize your program, a compiler would first analyze your program. There is a huge research area called program analysis. So a JIT would perform program analysis and identify opportunities for optimization. As JIT compilation has overheads during the execution of a program, typical JITs would perform very imprecise program analysis. Let us say foo calls bar, the compiler will not spend time looking inside bar. It would just say, I don't know what happens inside bar. I would just look within a method or within a basic block and optimize code. Right? So it may lose opportunities for optimization. Now coming to one of the interesting points mentioned by one of you in the beginning, will GCC-O2-O3 beat standard JVM invocation? It might likely yes, because GCC would, when you optimize thoroughly with GC, you might spend a lot of time performing compilation. You might look inside all the methods you're calling up to a certain level. You might try to inline more methods and so on. Whereas in the Java world, since things are happening while the program is already executing, you might not try to do much of an inter-procedural analysis at least. So you might actually miss out some of the scopes for optimization that a static compiler will typically afford to be able to afford to perform, right? So how to bring, the idea is how to bring decades of advancements in static program analysis to the JIT world. Static analysis has had a lot of advents. How do we bring them to the JIT world? So we will take a particular use case and I will show you what kinds of things we are doing for the next 15 to 20 minutes. So we would try to optimize, since we discussed about O languages, object allocation, access and deallocation overheads, we'll try to optimize all of them. So now we'll move a bit quickly. So let us say if I allocate an object at line 4, I would call that object as O4. So if you see this program on your right hand side, we have 3 objects, O4, O5 and O6, all allocated by the new statements inside the method foo, right? And then we have a static field. Static fields are like global variables in Java. So any object that's reachable from a global variable can be accessed by other threads, right? It can be accessed outside this method by any other person who can access the variable G. Now, I'm sure you know that objects by default in Java are allocated on the heap, right? So all the objects are by default allocated on the heap in Java, and then garbage collector, which has its own overheads, clears them out periodically, clears the unused objects periodically. On the other hand, local variables, primitives, and so on, you keep on the activation record or stack frame of a method, right? The advantage of it is anything which is on the stack, you can execute, you can access it faster. You can access it just by some offset, constant offset from the stack pointer, let us say. And anything that's on the stack of a method, stack frame of a method, gets freed as soon as the method execution is over. So you don't really need to do any special garbage collection by a separate thread for anything that you allocate on the stack, right? So the question here is, can we allocate some objects on the stack? By default, all the objects are on the heap. They have their access overhead, allocation overhead, deallocation overhead. Can I allocate some of the objects on the stack? Okay, that's the question. The answer is yes. There is a well-established program analysis called as escape analysis that tries to find which objects in a program can be allocated on the stack frame of their allocating method. So let's define what is meant by escape of an object. So an object is said to escape its method of allocation if it can outlive the activation record of that method, right? Very, very standard. If an object's lifetime is less than the lifetime of its allocating method, I can keep it on the stack. The object does not escape the method. If it outlives the activation record, I cannot keep it on the activation record. I have to keep it somewhere else. Hence, I allocate it on the heap, right? So let's see here at line 4, I allocate object O4 and make it point to make the variable x point to that object. So we can say on the left side you can denote these points to relationships. You can say x points to the object O4, y similarly points to the object O5. O4 was pointed to by x. So when you say x dot f equal to O6 at line 6, you can say O4 dot f, the field f of object O4 points to O6. And at line number 10, notice you do g equals p dot f. You had passed x, right? So p dot f is basically O6. So g, the variable g, global variable g points to the object O6. So you could say that after performing escape analysis, you could say that O4 and O5 do not escape foo. See, O4 you are passing to bar, but you're not making it escape out of bar. Foo calls bar. So lifetime of bar is less than foo, lifetime of O4 is less than lifetime of foo. Right? O5 you are not passing it anywhere else, so it doesn't escape. Whereas O6 escapes at line 10. It becomes reachable from a global variable. It escapes the lifetime of foo. Is it clear? So based on this, if I want to allocate objects on the stack now, what all do I require? If I want to allocate O5 on the stack, I require an intra-procedural reachability analysis. I need to look within foo and find out that O5 does not escape foo. In order to capture O4, I require an inter-procedural analysis. O4 is passed via X to bar, so I also need to look inside bar and find out what happens to the parameter P, the object O4 over there. And O6 O6 does not escape until line 10, which means until the call to bar at, inside foo. It escapes afterwards. So I could have allocated on the stack before the call to bar and so on. So I need to really model the flow inside a program. I need to know that until line 7 or until line 10 it doesn't escape and afterwards it escapes and so on. So I need to do a flow sensitive analysis. Right? So this is what would be required to optimize in terms of stack allocation for this code. But as we said, JIT compilers don't have time to perform all this precise analysis and so on. So what would happen is typical JIT compilers would afford only imprecise analysis. They would not look inside methods. They would not be flow sensitive and so on. As a result, Hotspot, which is Oracle's JVM, OpenGen9, which is IBM's JVM, their JIT compilers can stack allocate O5. It's a very local object. It's not passed anywhere. If bar is inline, then they may be able to allocate O4 as well, because now bar is inside foo, so they can just as inline. They don't need inter-procedural analysis. They can still stack allocate O4, but maybe nothing about O6. And if bar is not inlineable, nothing about O4 either. So existing JIT compilers allocate very few objects on the stack because of the virtue of their imprecise program analysis. All right. So what do? We look at an opportunity here. We see how our Java programs translated. Now we said there is this JIT in the JVM, which has this overhead of JIT compilation, and hence you don't want to spend too much time there. But we also have this static Java compiler, isn't it? Can we perform program analysis statically on Java bytecode even before executing it inside a VM? Or how much analysis can we perform statically without reaching the VM? That's a question we asked ourselves a few years ago. And we developed, at least when I was at IITM, I developed, as part of work done at IITM in my PhD thesis, we developed this PI framework, precise yet efficient framework, where what we said is analyze applications and libraries independently in Suite. Suite is a static analysis framework. So we would analyze Java applications statically as much as possible. You know, right? Of course, you don't have runtime values. You do not know the values of variables, types of variables, and so on. So you can't do everything statically. Do as much as possible statically and merge the results during JIT compilation. Make the best of both scenarios, both static analysis and JIT time analysis. The advantage is this way you can have the results of precise analysis in the VM without much JIT cost. So do as much as possible statically and improve things at runtime. This is the idea over here. And let us say we apply this idea for stack allocation. What does it mean? Perform whatever precise analysis you want to do, flow sensitive, inter-procedural, context sensitive, everything statically before running the Java program. Store those results, let's say in some separate files or some extra information in the Java class files. Use these results to perform stack allocation of a large number, potentially large number of objects during JIT compilation. Let's say this is the idea. The idea is well and good, but now we have a trouble. What trouble? If you were, let's say, doing static analysis before running the program, you cannot support some dynamic features. So languages like Java nowadays support various dynamic features at runtime. For example, there is a feature called hot code replacement. What does it allow you to do? While running a Java program as part of a debugger, you could also change the code, right? If you change the code, you could make an object that was earlier local, earlier non-escaping. You can make that object escape now. You can add a new method call that assigns that object to a global variable, let us say. Right? So you could change the code at runtime. You have features like dynamic class loading that may load new Java code at runtime that did not exist statically. So what would happen? Static analysis results may go wrong, isn't it? If I kept something on the stack, and at runtime somebody has made it escape. Now if I try to access it from the stack after that method is popped off from the runtime stack, I may get an invalid address. The program may become wrong. It's not acceptable. So how do we handle this problem? First, when we reached out to Oracle, they were like, no, 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 you really can't use static analysis results in a VM. There are all these problems due to dynamic features. No. Then what we said is, we can actually use the static analysis results. And is it possible to invalidate these results if needed? Can we detect that something wrong is happening at runtime? That an object that was earlier non-escaping is just about to escape? And can I repair the memory allocation while the program is already under execution? So we reached out to IBM with this and they were very happy. They said we should call this optimistic stack allocation, that we would optimistically keep objects on the stack based on static analysis results, and we would move them. We introduced this term called as heapify. We would heapify the object, we would move it to the heap if we find that the object's lifetime is going to be longer than the lifetime of the allocating method. So we let me go a bit deeper. Let's say we treat the static analysis results as hints and perform stack allocation optimistically, and the process of checking whether an object should be moved onto the heap, and if yes, then it is moved onto the heap. It's called dynamic heapification. So we detect at runtime if we have stored a non-local object wrongly on the stack and then heapify it, right? Notice that if I move one object on the stack, its fields, right? If via its fields I reach other objects, I need to move those objects also onto the heap so that I do not access them wrongly again. All this requires modifying the code generation routine of the compiler, of the JIT compiler, so that it can add these checks at runtime and this heapification routines at runtimes. If I had such a scheme, what could happen is both objects O4 and O5 can be allocated on full stack frame without any JIT analysis. So let's talk about this heapification in a bit more detail. What would happen? Notice that these checks are performed at runtime. I need to check whether an object is wrongly on the stack while the program is executing. I am inserting this check as part of the code gen routine of the compiler, right? So how often, whenever an object can be stored into something, whenever I am returning an object from a method, I am making it go out of scope of the method. Whenever I'm passing an object through a throw statement. So basically, whenever an object can go out of the scope of the method, I need to check, is this object inside this method scope or not? Right? So for example, the check may look like this. If I have a statement a dot f is equal to b, a field store statement, I may want to check if the object pointed to by b is on stack. If the one pointed to by b is on stack, but the one pointed to by a is on the heap, that means b is reachable from a. So I need to heapify it. I need to move the object from stack to heap. Else, let's say none of them is on the heap, but both of them are on the current stack frame, then I am happy. Both are in the current method's local environment. Let us say A and B are on the same stack frame, I don't need to do anything. If they are not on the current frame, but they are higher up, somewhere up on the current, on some the same stack frame, I don't need to do anything. But if A is on a stack frame that is popped before B's, that is also okay. What's the last case? If A is on a stack frame that is popped after B's, A's lifetime is more than B, then the object pointed to by B cannot be kept on the stack. Its lifetime is longer than the stack frame, and hence I need to heapify, right? So all these checks need to be performed whenever I have a store statement a dot f equal to b at runtime, which is quite expensive. And notice the last three bullets require you to walk up the stack frames. You need to go over the runtime stack, find where is the left hand side object, where is the right hand side object, whose frame is popped before the other one, and so on. It's very expensive potentially, isn't it? So how do we, the last trick of the trade here is, how do we reduce the cost of these checks? Okay. Notice, A is not on heap, let's say, and neither are on the current stack frame. I do not know where are they. I need to go up other stack and find where is the left hand side object, where is the right hand side object, right? So if I were in cases 2 and 3, notice, if I were in cases 2 and 3, I don't want to really find out where are the objects, but assuming it is one of the two cases, I am just in some below stack frame where I have this a dot f equal to b statement. What could I do? I could just compare the addresses of A and B, isn't it? If the addresses are growing towards decreasing addresses, then if A's and I have the statement A dot F equal to B, if A's address is less than B's address, that means A's lifetime is lower, it's lesser than B's lifetime. So I don't need to do anything. If A's address is greater than B's address, that means B lies below, and hence I need to heapify. So the last two cases, just an address check will work. It's not expensive. The only trouble is if A and B are on the same stack frame. The question we asked ourselves is there a way I could perform a cheap address check and without knowing where are A and B, even if A and B were actually on some other stack frame, on the same stack frame, how can I perform a fast address check? Right? So the point is, this address check would work even for the first case if B was placed on the stack before A. If I had A dot F equal to B, and I even if they were in the same stack frame, if I place B before A, that means this address check can be used later to determine if B needs to be heapified. Is that clear? So this was our idea here. We said we should go over the points to relationship established in a program, go over all the statements and find out in what order should you allocate objects on the stack. Whenever I see A dot F equal to B and A and B are in the same method, I should declare that at runtime, the JIT compiler should place B before A. The address of B should be less than the address of A. Simple enough. So we call this idea stack ordering. And what would happen if these checks are sufficient? We may not have to walk the stack much. We may not have to perform those expensive stack walking routines. We may not have to invoke them in order to find out whether I need to move an object from the stack to the heap. And that's an achievement in itself because it reduces the amount of cost that you have for heapification checks. Right? So just recollect what did we achieve. We could now perform static analysis, identify a large number of objects that could be placed on the stack, optimistically allocate on the stack, modify the JIT compiler's code gen routine to insert these checks at runtime. We have a special way of allocating objects on the stack so that these checks are not much costly. So we get more object allocations on the stack without much cost at runtime. Which something which the JIT would not have been able to do without performing a very expensive analysis that might interfere with the execution time of the program, might affect it negatively. Okay. So that's about stack allocation. I did want to go through a couple of more optimizations, but I think we might run out of time. I would rather better take some questions later. So I would just tell you what kind of optimization what kind of more optimizations may exist. Let's don't read the slides. I'll just show an example here. So we had this object O6, right? The same example is there on your right hand side, which can be kept on the stack until line 7. But usually compilers don't keep objects on the stack partially. They would keep them either on the stack or on the heap. So what we said is we could replace the object with constituents. If an object cannot be placed on the stack after a certain point, until that point I can just throw away the object. If object has 2 integer fields, I could just use those 2 integer fields until the point it escapes. When it escapes, I'll keep it on the heap, allocate an object and send it across. This idea leads to another optimization called as splitting the range of replacing an object with its constituents with scalar fields, and this is something further that we do. There is also an upcoming feature in Java that's called object inlining. You can place one object inside another so that you don't have indirection in accessing that object. So we are trying to come up with a strategy to inline such objects inside their container objects. I'll not talk about it. Please feel free to go over the slides later and reach out to me. But the point is, all these optimizations, stack allocation, scalar replacement, scalarization, inlining, and so on, they reduce the cost of object allocation, deallocation significantly to the point that we are able to observe significant performance improvements. By significant, I mean up to 5% to 10% performance improvements in Java programs. The Java programs run fast, but they are O has its cost, and now we have come up with several new kinds of optimizations or new ways of performing optimizations in the Java world that can lead to the programs running even faster by avoiding a lot of the overhead associated with OO programs. Okay. So I'll talk about some non-technical aspect maybe for the last 5 minutes, but we can take any questions at this point. Anybody has any question related to whatever I talked about, we can take it here.
So you explained once again in the last, like the previous slide where you explained in the first case, only when I think when only when B was pushed in the stack before A, you could do that address comparison. Like when A and B are on the same stack. Why can't
Yes.
it do it when in the other case? I didn't really understand that.
In which case?
The first case, case one.
Yes. So see, if I do not know where are A and B, right? Unless I walk the stack and find out where are they, I cannot really compare their addresses and conclude anything, isn't it? If I did not enforce this property that if my program has A dot F equal to B, then B should be allocated before A on the stack. If I did not have this property, an address comparison cannot tell me anything. An address comparison cannot tell me whether I should heapify the object or not, unless I actually go and find out whether they are on the same stack. Did I answer your question, Pranav?
Yes, sir. Yes, sir. Thank you, sir.
There are a couple of questions in the chat window. Doesn't static compilation not make any assumptions about the inputs? Okay, I think this has been answered by the way we handle the possible challenges. Does it still remain platform independent? Yeah, so Manoj, many of the optimizations that we would do this way would still be platform independent. Let's say we are not doing anything specific to the machine, just deciding what object should be on the stack and in which order is not dependent on the machine. Of course, yes, there if you do something that's dependent on the platform, you can't run it as it is on different machine. Does this kind of in a sense, yes. So when we don't have a strict type system, we would be able to let's say we don't know what kinds of an object can be pointed to by what. So we perform a general pointer analysis for C++ programs, for example. So where here I know that a variable of class A will be able to point to only objects of class A or the objects of classes that are below class A in the hierarchy. But in C++ programs, this you don't have this restriction, right? So anything can point to anything. So the pointer analysis as such becomes a bit difficult in the sense its precision may not be as high as I could get in Java programs with a strict type system. But the analysis is still possible in other languages as well. It may just be a bit imprecise. I hope I answered your question.
Uh, I have a question in the object inlining part. Can I ask?
I did not really talk about it, so I think
Okay,
yeah,
okay, sure.
if it's quick, we can go ahead, else we can talk about it later. It's a new optimization, it's a new feature coming in upcoming Java versions, and it leads to performing new kinds of optimizations that we are doing here. We can discuss it at the end.
Okay, sure.
So getting all of this work, of course, if you feel it's a lot of work, it is because a lot of people are involved in this. Apart from people from academia and industry, there have been lot of students, BTech students, MTech students, PhD, masters by research, all of them you see on this slide who were involved in this object allocation, deallocation, speed up work, optimistic stack allocation work. And we have been getting outcomes. There are papers, there is a patent file, uh, we are also working on things which are not Java. So we are also reducing the JIT overhead for R. We recently, after 2 weeks, we have a paper presentation in UPSA 2023 on that work, which means more students were also involved. So it's not just like we have been doing Java work, but JIT has a lot of interesting challenges, and we have been trying to solve many of them in the last few years. The interesting thing is most of the work that I have done, or probably all of it, is in real world compilers and popular analysis frameworks. It makes it challenging to do so, but once you do it and you can really see your code actually executing in a particular VM and improving something, you really feel happy. So I will end the technical part with a simple question: which programs are the fastest? We started with a code demo. The answer is not really. None of the programs is fast by default. It's the compiler that makes programs fast, at least in this context. And the research area compilers and improving the optimizations performed therein is really interesting. There is a lot of scope, and we have been utilizing some of it in the last few years. Uh, Sir, do we have a few minutes or shall I just conclude? I just wanted to talk about some non-technical things. What
That
have I
will be very helpful, Manas. Please go ahead.
Okay, so I'll try to keep it small. Some of you may know me already, particularly one or two people were from Pace Lab. I saw the news. I basically did my PhD at IIT Madras from 2013 to 2019. I was a direct PhD scholar, later made it a dual degree program. Then I joined IIT Mandi in 2019, and recently, last December, I moved to IIT Bombay. You see an emphasized family there, along with the entire family. I'll talk about it. So this is completely an experience-based stuff that you should be able to relate to. Some of you may be able to relate to. So the first stop was in this journey was IIT Madras. I joined IITM due to when I reached Chennai for the first time. I was traveling to the south, and in the bus that I took, 5C bus from the central station to Taramani Gate, there a lot of people came, lot of several ladies came with this jasmine flower, and I really felt happy. I just felt welcome, and that was my first interaction with Chennai. My first interaction with IITM itself was very good, in a similar way. I really liked my interview, the way 15 to 20 professors are who interviewed me during my interview, and I really just joined IITM after I got the offer. So I had a slow but steady start of a direct PhD. Since some of you might be PhD or MS students or planning to do so, there were initial shockers, like some of the subjects were too tough. I dropped compilers course in my first semester, if that surprises you enough. Uh, then I submitted my first paper at the end of my third year, but it kept getting rejected. It got accepted finally at the end of my 5.5 years, soon after which I finished my PhD. I had two postdoc and two industry offers without even applying. So good work and patience over there helped. I chose to stay in India. I decided not to go abroad for the postdoc and the offers. Of course, I made a lot of good friends, got an inspiring advisor, unwavering support from teachers and mentors. Professor Anderson and Professor Rupesh both were there in my committee. I started writing about monkeys, and you know all the beautiful things about being at IITM, right? I learned yoga there and so on. So I had a very good start at IITM, I would say. After that, I moved to one of the most beautiful IITs, perhaps IIT Mandi, where I joined in 2019. Just thinking, okay, enough with hot climate. Let's try the coldest IIT. I wanted to make an impact. I got enough opportunities to do so there. Being in a new IIT, you get to offer new courses. You get students who didn't have some of the courses, exposure to some of the courses. So it was a beautiful journey over there. I became a sought after teacher plus mentor of the sorts. Like a lot of people, I had to say no. Then I got a teaching award in 2021. That was because my courses were getting the highest TCF, the highest feedback across the whole institute, across all the departments. So that was an achievement. I really, sir, I won't agree with your comment, but let me come to that. And then I also learned there how to bring research outcomes with BTech students, because at a new IIT you do not usually get too many PhD and MS students. So much of the work that I showed to you was done by BTech students as well. Since some of you are doing BTech, there is a lot of scope for in research as well, that if you take some time out of your schedule, right, you can do wonders even in a BTech program. Of course, masters and PhD students, you have to do wonders. So basically at Mandi, my three priorities were just work, work, work. I did a lot of work and it paid off. Finally, though it was a bit far for me. Mandi was turning out to be a bit difficult in terms of travels and my family. So in December, I moved to my favorite metropolitan city, which is Mumbai, and I have relatives here. Travel was easy. All of you know it's a brilliant CSE department. I actually used to doubt whether I would be able to make it, or what does it need to be able to make it here. Another challenge was that I had students doing masters, PhD projects with me. What to do about them? I never wanted to leave anybody in the middle. So that was one question. I talked about these questions to the people working in my area at IITB. They encouraged me to apply, saying that most problems can be solved. Department made a strong recommendation. I had a strong selection panel. Finally cleared the interview. Everything good, and that family part. So I was able to. IITB was very helpful. I was able to shift almost all my students in some form or the other to IITB. So nothing lost, no regrets, and probably I'm not going to move soon. Which means any of you who are interested to work in this area, please do contact. Please also include, of course, IITM is one of the best places. Please also include IITB in the list of places where you want to be at or do some work in collaboration with. So few takeaways from my talk would be: do not be afraid of taking your decisions. I have made choices like do not go for a postdoc because I did not want to go, even though everybody wanted me to go. I think it was good not to go because then the COVID years came, right? So I had personal reasons and I couldn't have come back to India probably for a couple of years. It would be terrible for my case. Try to do things honestly. That's something I would always tell my students. I have seen enough plagiarism and dishonesty cases. Don't do that in research, at least. It would be very critical. There is no shortcut to hard work, but as you saw, hard work really may pay off, right? So when you have to work with a complex compiler or a real-time system, it requires more effort, of course, but it really educates you. If luck works, you might get papers soon. If it doesn't, then also you are going to learn a lot, which will pay off later. You can tell at least that you have real experience with real compilers in my case, for example, and enjoy the process. In compilers particularly, you enjoy the process because you get to even work with all these interesting new tools, right? Interesting IDEs, interesting debuggers. It's real fun to be able to see how does a system work, how are things really happening when you run a program, for example. And then, since I talked about not getting a paper for a long time and so on, I'll tell you humans are extremely capable. Life has no limits. So don't judge yourself. This is also one learning from my own experience. Don't judge yourself by failures or one or two failures. If your efforts are persistent, you are doing something sincerely, that's enough. One thing I always say is play with these binary machines, these computers, but don't forget that life is fuzzy. So keep that in mind while you still strive for hard work. And of course, I will end by saying compilers and programming languages are a very active, vibrant, and interesting research area. Anybody who told you otherwise is behind by 2 or 3 decades. There is a lot of interesting work happening all over the world, and particularly for systems that are heterogeneous, multi-core. Even theoretical work on formal methods, program analysis, verification. There is a lot real work happening, and there is no end nearby that you can see. So yes, so these are the areas where my group works here. We work with static languages like Java, speculation in JIT, and so on. We are also working with dynamic languages like R, Python, JavaScript. We are trying to create IDE plugins for parallelizing functional code and so on. We are also trying to make the life of compiler designers easy by creating debuggers and visualization tools, not for particular programming languages, but for particular compilers, which may help ourselves and people like us. So yes, join us and become the next compiler who can work on compilers. Thank you.
Thanks a lot, Manas. Anybody has any questions, technical, non-technical, feel free.
One student had a question about object inlining. If it is quick, I can maybe take it now.
Yeah, sure. Naveen, you want to re-ask your question?
It might overshoot the time. So if that's fine, I'm ready to ask. Like
Okay, so
I can push it to I can push it to the last.
yeah, sure. If there are any other questions, we can take those up. After that, I'll stop the
That's one
meeting.
question. Like currently, what kind of optimizations happen in Java C? You said that program analysis, etc., doesn't happen as of now. Like you were inventing on it. So what
Yes.
really happens there? Like what kind of optimizations are allowed there, and what currently happens there?
Yes. So, as such, Pranav, anything that is machine independent is allowed per se, but traditionally, JITs have been, I mean, JIT-based systems have been relying on JIT compilers to do most of the optimization, saying that, okay, anyway, JIT is also one-time effort, right? You JIT compile, unless your speculation goes wrong, you could possibly use JIT compile code several times, right? So the assumption is that even JIT compile uh, relying on the JIT compiler for trivial optimizations is not a very bad idea. But Java C, just to answer your question precisely, Java C indeed performs simple optimizations like dead code elimination, like some level of constant propagation, some unreachable code elimination, not too much though. Of course, with the way we are performing analysis, We are not directly implementing things with Java C till now. We are collaborating with IBM on doing analysis in the Eclipse Java compiler, which is also a static Java compiler like Java C, but the ideas can be actually integrated into Java C as well.
Okay, sir. I had another small question. So when you said that in Java C or in a static Java compiler, you'll do this program analysis, and then you try to push these objects on the stack, and then you said that sometimes it will like not be accurate. So why won't it be accurate? I didn't really get that.
Yes. So as I said, let's say if your analysis implementation is correct, there is no inaccuracy or unsoundness in the beginning, but at runtime somebody changes the code or somebody loads code. So let's say you have a method called x.foo. Now statically x could point to only objects of type A and B, let us say. There were foo implementations in only A and B. Now at runtime, due to a feature called dynamic class loading, let us say you get a new class C that is also in the same hierarchy, but it never existed statically, which means if there is a new class coming up while running the program, uh, a new method could also come up, a new implementation of foo also could come up, where things may happen differently from what you assumed statically. That's what I meant.
So is this like possible in C++? No, right? Like it's only possible in Java.
I do not think dynamic class loading is supported by C++. I'm not 100% sure though. In Java, it is historical because originally Java programs were supposed to run on different machines, right? You transfer Java code over a network, so you can transfer new class files also over. So that's actually one of the reasons all the analysis used to happen inside the JVM in the JIT world, because you are really getting all the code that you want to run only in the JIT time. You don't have access to much of the code statically. But what we are saying is you have access to some of the code statically, probably a large portion of the code statically. Do as best as you can.
Thank you so much.
All right. So what I'll do is I'll stop the meeting now, but Manas and Naveen can possibly continue the discussion.
Sure.
Thanks a lot, Manas, and thanks everybody for joining.
Thank you. Thanks, Anishan sir, also for the comment. Thanks, Thakur sir, for actually inviting me.